Everybody. Our next speaker is Eldad Haber from UBC, and Eldad will speak about deep neural nets meets ODEs.
Hello, and thank you for the invitation. This is work which was done by myself, and then Lars is going to give a talk immediately after my talk, and we'll replace the O with a P. And Elliot, Lily, and Bo are in the Extract, which is a startup company in Vancouver. Okay, so I'll talk a little bit about deep neural network. This is not the most common thing that a lot of us in the mathematical sciences are dealing with, but it has been a semi-revolution, at least in the computer vision or in the machine learning work, and it appears right now in the newspapers. Maybe because now I work on this, I notice it appears in the newspapers almost every week. There is an article, usually in the front page of some newspaper about it. So it's interesting to see what it's all about. So I think if those of you who don't know what it's all about, I'll try to give an introduction to what it is, and I'll try to demystify it, because there is a lot of myth that comes with this particular field. So I'll try to demystify it and talk notation that we can understand, and also explain that it's actually important for these notations. And I think I'm going to try to convince you here that we as a community actually have a lot to offer for the community who is actually doing this kind of work. Then I'll of course talk about how these kind of things meet differential equations, and what's the connection between deep neural network and differential equations. And actually there is a very natural link, and this is where we can contribute a lot to that particular work. And that of course leads you to the idea that you can actually build different type of neural networks. And I will give examples, future work, and then I will actually maybe lay the ground for the talk after me, which is Lars, which is going to really do the real work, which talk about PD. I'm just a warm-up band right now, so that's going to be, he's going to do the real thing. Okay. So I'm just going to give a quick overview here. So what is deep neural network? Well, it's just neural network. So if you have not seen it, I'll explain what a neural network in the next slide or two. But it's just with a special architecture, which is deep architecture. So that means that it's a very long network. It exists for a long time. There's just a question. I mean, the 50s were invented, and then people start using 1 layer and 2 layers and 3 layers and so on. And the question, what is deep? Well, we'll get to that particular point soon. But people have used more layers since the 50s or 60s, and then recently used many, many more. And for large amounts of data, they seem to be working very well. So that was really where about 5 years ago, I mean, people knew about this for a very long time. I'm sure a lot of you guys here have, seen this thing before, and it was this kind of field that was there. Like, we all know how to do this. But about 5 years ago, people managed to break some of the big problems in computer vision with deep neural networks. And to be honest, when I started working on this, I did not appreciate how tough these problems are. So some of these problems of identifying, for example, a data set like CFAR10, which is a natural image data set, or ImageNet, which is 1 million images that people try to classify, I looked at this and said, well, it's just, you just apply the thing and you seem to be working. But then when you start actually trying to do it yourself, it makes you a little bit humble about, what you can actually do and what you cannot do. Computationally, it looks like straightforward, but it doesn't necessarily work that easily. So the fact that they managed to break it about 5 years ago really make a big impact. So recognizing images, for example, ImageNet is a set of 1 million images, natural images. People take, it's dogs, it's cats, and the types of dogs and stuff like this. And then the success rate was in the 70%, and it went to the 90% in something like, in the course of something like 5 years. So, and a lot of the images are actually difficult. When you look at the images, you realize it's not just a dog. They give you the type of the dog. And those of you who are not really dog lovers and identify different types of dogs, it's going to be pretty tough to know exactly what type of dog it is. But, these kind of networks can do these things successfully. So this was the big breakthrough of this thing, and then people say, well, it works. Google came with TensorFlow, Facebook came with Torch. Now you can just go ahead and make it work, but we don't really know exactly how it works, so we'll talk about this as well. And then it works really well, okay? So the application, again, image classification, face recognition, so all your Facebook face recognition is done by this. Image segmentation recently, driverless car, people are now using this, and there's going to be a whole more application people are coming up to do with this. Just, a few recent quotes, and I should actually try to update. I prepared the talk for this one this is a slide I stole from a talk I did 6 months ago or so this was 2016, and there are going to be new of them in 2017. Again, every week or two you'll see something appear in the newspapers about this. Okay. However, MIT Review had an interesting kind of more popular science article about this, and they claim, and rightfully so, that, no one really knows how these algorithms work. And that can be a problem, especially when you start thinking about, it's one thing about identifying cats and dogs, it's another thing when you're doing a driverless car with it and you think that your car is going to be driven by an algorithm that you don't really understand what it's doing. So that's the next thing. There is apparently we're in Europe right now, so there is a new thing in the European Commission that put together some kind of rule that now you have to be able to explain what your algorithm is doing. And this is a problem because you can't explain what these things are doing. Okay? So this review will say we build these things, but we don't know how it works, which is, by the way, the classical engineering thing. We build things that don't know how it works. Of course, scientists is what we are. We build things, we know exactly why it's supposed to work, but it doesn't work for us, correct? That's a big difference. Okay, so starting to look at a more structural point of view, this is how you see a lot of neural network talk will talk about input layer and some connection and output layer. One of the first things that is one of my pet peeves is actually this picture. I really don't like this picture, and I think that we should start avoiding this picture as a start, and we should really start thinking about what is this thing represents. Well, this represents a matrix, correct? I have input, and basically whatever comes here is what the thing that comes here is this guy plus with weights from here plus this guy with weights from here. I think we call it a matrix. Okay? We learned that this is a matrix long time ago. So we should really say that this is a matrix that operates on, take this layer and operates a matrix on this one. And then you apply nonlinearity, add some bias here, and you get the next one. Now, why I like this one much better than this one is because matrices, most of us, I don't have to tell you this, have structure. So if this matrix is going to be an M matrix, I have a problem to represent it as lines. If this matrix is going to be an H matrix, it's going to be symmetric, anti-symmetric, all these different things that matrices can do. When I see this, I can start thinking about what these matrices are. When I see these lines, well, I don't know how to do this. Besides, by the way, it takes me much quicker to do this, to write this, than to write this. So I don't know why would you like to have a structure that takes so much time to write compared to something you can write in a second. So I think that we all have to start realizing that I've not been to a linear algebra talk that I've seen this picture. Jim was last time, did not give me this picture. He actually showed me matrices, which is obvious for us. So we should start, modernizing that thing and start saying, wait a minute, we're not really dealing with lines and squiggles and stuff like this. We have matrices and we have vectors and we have nonlinear functions and we understand how to use them. So I would challenge the first thing to do is to really think about it in this particular way. And by the way, this particular thing that's the old neural network representation, which basically tells you that you have a network where you start with some kind of y, which is going to be y0, for example, in the first layer, which is your data. You're going to take your y0, you're going to multiply by some matrix k, you're going to add some bias b, you're going to apply nonlinear function sigma here, and that will give you your next state. And you can apply it on and on and on. So a single layer neural network will be only doing it once, but if you have a long, it can be 100 or 1,000 of those until you get to the final state, and then you'll do something with the final state. So now let's talk for a second about what is the residual network and then what the problem is. So recently, again, this field is moving quickly. In 2015, Microsoft came with a new architecture, and the architecture looks like this. I'll slow a little bit for this particular architecture. It's almost like the previous one. So remember this, we had the first one was just this part. Okay, but what they did is they multiplied this one by another matrix on the side here. Then they added the initial state here, and then they put another function here, another what they call activation function here at the end. Okay? By the way, you will not hear from me saying that I'm recorded, correct? That's going to be on tape here. I will not hear from me that this is similar to the brain. I have strong doubts. I can say inspired by the brain. I have strong doubts that there's any similarity to the brain. Things that run on this particular hardware have to be in silicon. I have a hard time to believe that it's similar to whatever runs on anybody's gray matter. It's not. I have strong doubt that this is even similar. So.
Those two sigmas the same thing? Are they both the same nonlinear function?
They don't have to be, but in principle, almost everybody is using them to be the same. Okay? But we got rid of this one immediately. So this is the architecture that they use, and they show that they can actually get much better results than previous. So this is again only 2015. So we actually started from this particular network. It was very obvious to us that this is the right network to use somehow. And then we did a modification. So one of the things, by the way, because the field is very sketchy in a sense, you try something. There is a very nice talk. There is a guy named Andrei Karpathy. He gives really nice talk, and you can download them on YouTube if you ever want to look at this. And he says, if something works, don't change anything. It's like if it works for you, just that's the obvious thing. If it works on something, try the thing that works. We decided immediately to wrap up everything, to change everything. So the first thing we did is we want to break it, so we removed that sigma up to see if it breaks. Didn't break, so okay, that's great. Then we said, okay, you know, why don't we add a small h here? I think for most people here it should be clear why we decided to do this. I mean, what do you care? If we call it 1, then we're all fine, we're all in the same place. And that's the network we decided to use. So we propagate with this rather than with this, and we immediately seen that it doesn't really change much what we're getting out. So the question is, so you propagate, you take the data, you propagate, you get eventually to the end, you decide that you propagate 100 layers, you propagate 100 layers. Question, what do you do at the end? Well, what you do at the end, you take the data that you propagate at the end, you multiply it by another matrix, which you don't know necessarily what it is, and you get something which is going to be C, which is the class, okay? So if I give you known classes, so if you know what the classes are, I expected in the least, if you think about least square classifier, it doesn't have to be least square, that this is supposed to be equal to that. That's the simplest way to think about it. There are better classifiers than least square, softmax, which should base on probability. But if you think about least squares, because it's the easiest way, at least for me to think about it, is what you do is you take the data, you start at y0, you propagate through that network as many layers as you want. When you finish propagating, you get that, you choose a matrix W, you multiply by this guy, and you get C. C is supposed to be your class. If it's the same, that is the class you have, you're happy. Now, why is it good for? Because if I manage to classify, if I basically manage to find parameters that I give you the data, give you y0, and I give you, and I find this K1, K2, and B for every layer, and I find the W as well. If you give me a new data, then I will take the new data, and I will basically go through the network. I will multiply by this W, and I will find out what the class of that data is. So if there's a new picture I have not seen, I will be able to propagate it through the network, multiply it by this W, and it will predict what this new picture is, which is what I'm trying to do in this whole, I mean, that's the reason why we're doing this. Okay, so here is maybe a final list of what I have here. This is the network itself. This is the names of these different things. So you have the matrix weight, the bias, the classifier, and then the forward problem, you're giving me one image basically, or many images, so I give you y1, and you find this class. So you propagate the whole thing, you give you a class. And in the training process, I give you many of those images. So I give you, by the way, I start with index 1 here because, of course, we're MATLAB users. So you start with this y1, you propagate. You know what C is, so you know y1 and you know C. And now you want to solve or optimize somehow for these weights, for this kj, bj, and w. Okay? So approximately giving you the right classification. That's the basic. I mean, that's it all. I mean, I don't really have to teach you anything else. You now know everything about it. Everybody can go ahead, do their least squares or whatever optimization problem you want to do, and do your own problem. Okay, so you can do this. It's straightforward. See? Okay, so I can write this whole thing as a problem. In general, people don't use least square. They use something which is called the joint entropy. So this is going to be the joint entropy measure that I have here, and this is going to be my ODE representation. In a second we'll talk why it is. And now what do I have issues? Well, I have issue we call stability and lack of generalization, so I need to explain what generalization is all about. I'll talk about a little bit about many solution and about robustness. So these are the main issues that we have to talk about. Okay, so let's first talk about generalization. And this is, I think, where we still don't know what's going on. Like I don't think anybody can really understand it. There are a bunch of papers about it, but none of us can really get a firm understanding of this. So this is where the magic really happens, and this is where usually, it's majestic. So one of the things that I have a pen here, if I drop a pen over here and I measure the acceleration and I have a model to make this thing work, so it will be 1/2 gt squared is equal to to the distance that it goes. I will do this model over here. I go to China, I do the same experiment. I will get the same G. Everything works the same, correct? Everything should work. So generalization of physics-based models is straightforward. I mean, we don't really have to even test the equation under the same conditions. So, for example, the fact that G is the Earth constant, all I have to do is if I go to any other planet, all I have to find is the gravitational constant of that planet, and the model works, correct? It's going to be whatever G of that planet, T squared. Right? So that works. So these models always work because they're based on fundamental physical understanding. Here we have a model. Okay, how did I get this model? Like this. Right? This does not tell me that this model is supposed to recognize cats and dogs. There is nothing about this that tells me anything to do with cats and dogs. I came up with this model yesterday, right? 6 months ago. Okay, and now I'm claiming that this model is going to recognize cats and dogs and do the difference between all these things. So clearly, if you have enough parameters in the model, you'll be able to do it, correct? I mean, we all know if you take a problem, parameterize it to death, we will be able to fit anything to anything. We're good in data fitting. We're big kids right now, right? But on the other hand, there is a question now, I give you new data, will it fit that particular new data? Now you can claim if the old data look like the new data, then everything will be fine. But if it doesn't look exactly the same, will it still work? And this is what people call generalization. So the basic idea is, again, I give you basically Y1 and C. Now I give you another set of data and another set of labels. And the question is, can I predict this one? Now, again, if it's very similar data, sure, everybody can understand this. But what the magic was here that happened, that people managed to show that it works even for things that are not so obvious. So when you look, for example, at pictures of dog and they look not the same, not from the same angles, not from the same thing exactly, and you show another picture, for some reason it identifies them. Now, again, I don't know exactly why people try to explain it. I don't think we still have a good understanding of why it can do this, but we are getting better in terms of explaining a little bit why it works. But this is really the holy grail of this whole field. If anybody could solve why things generalize, then they'll be rich and famous. So that's the big thing. But so again, we're trying to understand some of this particular phenomena that works well. Okay, so again, once again, I mean, we don't know why things are working well. There's issue about, I mean, people hypothesize about minimas and maybe local minimas and global minimas. There's some papers about this. But again, no real solution to that particular problem. Okay, so this is more or less the background that I come up with this talk. And what is our goal? Our goal is to understand the problem, of local minima, generalization, all these different things that are happening. And if we understand something, then we're going to be probably less in the dark in terms of these algorithms know, but we have no clue why. We can suggest better algorithm to make it work better with less data and to do better things with this, okay? And of course, if you already know how things work and you can connect it to all the other stuff you've been doing, you can suggest, for example, better optimization algorithm. You can suggest a lot of new things. So I think we're just in the beginning of this journey of trying to import a lot of the technology that we know from scientific computing into this particular field. So I'll try to convince you this is the case. So first thing, let's look at this particular comparison between deep neural networks and ordinary differential equation. So remember I added this h, and now it should be clear why, because if you take this thing to the other side, divide by h, you get an ODE. Okay, it's basically a forward Euler discretization for this ODE. So you have basically these K1 and K2, these are matrices that are changing in time in principle. And what they do is they basically take the initial data and move it all the way to the end that you can classify it. Now I need to show you a movie on this to make it simple, or maybe not so simple. Okay, so I'll go over this movie more than once. First, let me stop here. So what do we try to do when we classify things? Classify things basically means you need to put a line and you need to separate these two groups. So if you think about what is this data, let me maybe a bit slower. This data is I have x, y, that's my data, just x1, x2, so x, y. And then I have a color, correct? That's my label. So given x is going to be something, y is going to be something, you get blue. And x is going to be something else, y is going to be something else, you get a red. So if you think about the data, it's going to be a list, x, y, color, correct? And I can just go ahead and take this data, and in 2 dimensions, of course, it's easy to plot it, and that's why I work in 2 dimensions. If you think about classifying images, so I'll show you one set of images at the end. I mean, if you have a 28 by 28 image, it's already a 700 and something dimensions so I cannot really plot the data as a point in space and think about how it moves. But in 2 dimensions, I can definitely do it. That's the nice thing about doing it in 2 dimensions. Now, what is a classifier? A classifier, a simple classifier, basically puts a straight line. So you try to put a straight line and to say whatever is on the left is red, on the right is blue. Okay, that's what you're trying to say. Is that really true for the Democrats and Republicans, or the other way around? So I need to just put a straight line. Now clearly here I cannot put a straight line to divide the 2 things, correct? I mean, I can put a line in any direction that I have, and it will not separate the groups. Now what do I have? I have an ODE, which is basically a dynamical system that takes these points and moves them in space. And it moved them in space, well, until, I think this movie is, until in principle, this one is, for some reason the movie doesn't, until in principle I can pass a line. In this particular case, as you see, I don't have a perfect classification. Until I can pass a line, and this line puts the red point on the top, the blue point on the bottom, and now you can say, okay, I can now classify my points. So every point is going to be classified to either red or blue based on the line that I'm going to find. The line is the W, correct? That's the linear classifier that I'm computing. And the K's are going to determine, the K's and B's are going to determine the dynamics that I'm actually taking in order to get to that particular case. So really, you can think about deep neural network in a very different way than people have been talking about in the literature. Thinking about it more like a dynamical system that take points from the initial condition they are, move them in space in some weird way, and you know, the dynamics is, again, we have conditions on the dynamics and get you back to something that is separable. That's really what we try to do. Okay. Now, let me get back to... Control L works. Yes. Okay. So again, the dynamics we chose to work with is this particular dynamic. So the difference between maybe this and some other fields that you've seen dynamics is that the K1 and the K2, I mean, they change in time, but the same K applies to all the points, right? So for example, if you ever looked at problem of image registration or basically flow problems, typically what happened, the Y here will have a matrix which will depend in space. So it will depend actually on where this location is. Here, no, I mean, the rules of the game is you have to find a K1 and a K2 that will be applied to all the points equally. We don't really differentiate between points that are in different locations in space. Again, two-dimensional space is a little bit misleading because if you think about high-dimensional spaces we're trying to work with, there are going to be thousands of dimensions, or sometimes millions of dimensions. So two dimensions is easy to visualize, but it's not really our goal. Okay, so again, you get something, you start with this and you get something like that, and by the way, that already tells you there is no uniqueness. For example, I don't care if I end up like this or like this or like this. All I care is that these guys are separable. There are multiple solutions. A lot of the solutions, you don't care that they are different. All you care is that you can do a linear separation. Okay. So here is the ODE, and now our first question was, I mean, so again, we're coming from an inverse problem background. And one of the things that you do when you do an inverse problem, you say to yourself, okay, I mean, I have a forward problem, correct? So nobody in this particular community looks at the forward problem because they all go to learning. But we say, okay, we have a forward problem. The forward problem is the ODE. Now, is the ODE well posed, right? I mean, that's a kind of a trivial question. The second question is the discrete ODE well posed? So if I have this ODE, of course, it can lead, this is just a forward order discretization of that one. I mean, this can be well posed, doesn't mean that this one is, right? If I take H to be too big, it doesn't fit the discretization method. Forward order is not stable for everything, as we should know. So is that really well posed? And to my surprise, when we start looking at this, nobody even asked that question. So it could be that people are actually solving a, well, ill-posed inverse problem with ill-posed forward problem. Now, why would I like to have a well-posed forward problem? Well, maybe I should show next a few examples. So first thing, what is well-posedness? Well, well-posedness means a very simple thing, is that if I take my initial data and I add an epsilon to it, and I look at where I'm at the final stage that I'm at, this thing is going to be small. That's in a very rough description to instability here. So in some way, what would happen if I would start with initial data, which is noisy, I will get to a very, very, very different final conditions, which means that I will get a very different classification. That can be a problem if we try to understand the method of what we're actually doing, and I'll show you in a second that it actually is a real problem. It was actually in articles about this in a few of the papers recently, surprisingly enough. So this is something that we really want to understand, and this is something that we need to control somehow. And this is, again, well understood by this community. It was not really clear to anyone in the learning community that this is really an issue. Okay? So why is this an issue? Here's an example that people show. So now people are very keen about what they call adversarial network. It's now a special topic for this year, one of their big conferences. So you take a panda bear here, okay, and you add a very, very small amount of noise, and you get this panda bear. So, you know, especially in the resolution on this screen, you cannot really see a difference between this one and this one. And even on this one, it's really, really hard to see there is any difference in these 2 points, this image and this image, okay? So this classifies it as panda as 57% chances to be a panda. You add something like this, which looks like nothing, and this now is classifying it as 99.3% to be a monkey, okay? So you're adding something like this, and you know, it's kind of nice when it goes from panda to monkey on the zoo, but you think about your car classifying like somebody who's walking on the street, and you're driving a driverless car, and it classifies them as a person, or classifies them at, you know, maybe a bush, or classifying that doesn't exist, or something like this. That can be a problem, right? So this is really an issue. So it's not really just invented from nowhere. Interestingly enough, there were papers about it, were articles about it in all the major newspapers. So it appears all the way to the major newspapers. And for some reason, of course, I mean, we should expect from reporters to know something about stability, correct? That's something that is obviously. But nobody says that, the problem is instability. Just say there is a problem in the algorithm somewhere. Now, the other thing that you see is exploding gradients, vanishing gradients. This is the adversarial examples that people are talking about. Okay. So if you actually start looking at this particular thing, you'll find out that most neural networks are actually not well posed. What saves them is the amount of data. So if you have a lot of data, then clearly what you can do is you take this amount of data, you put it in, you put it out, then you just cover the space, and you're in reasonably good shape. So if you're training on millions of images, you should be more or less okay, even you're not stable. I mean, you just don't go far enough because you don't start too far away from wherever you need to start. But if you start removing them, then you'll have problems. So the question would be, how can we make the problem well posed? So that's in some way relatively straightforward. And now you can think about ways that I'm going to show you. Here's one you can say, let's constrain the weight matrices. Let's actually design new networks that are going to be well posed to start with. And we're going to make a discrete dynamic well posed as well. Okay, so this is it's not really a theorem. I should really be a little bit more careful because we made mistakes with this before. But this is really kind of trying to summarize what needs to be in order to make this thing well posed. So we have an ODE, y prime is equal f of y, where the f of y is a particular form. That was the particular f of y we saw before. And what do we need in order to be well posed? Well, we need the real part of the eigenvalue to be not positive. So we need them to be either 0 or negative. So the Jacobians is, for the transformation, needs to be definitely not without real part. And then we need the Jacobian to change slowly enough. If Jacobians change quickly, then things are in trouble. So this is the Jacobian in this case. It's actually very easy to compute. It's a matrix K2, diagonal of that activation function, which is always between 0 and 1 for all the activation function people use, and this one. So this is always positive, and you have these two matrices. So for example, if you choose K2 is equal to identity, then you can have that the real part of this K is going to be, if you choose it to be negative, then you can have problems. You have no problems, okay? And changing again, and changing slow enough between the layers. So this is just one example, but you can come up with many different things. And that, of course, leads to this idea that you can actually have, again, different architectures for the neural network, which is, again, hard to express when you have squiggles and lines. So, for example, if you have an antisymmetric matrix here, again, changes slowly enough in time, we have to quantify this somehow, then you can generate a stable network. So this will be a network with only antisymmetric matrices would lead you to a completely imaginary spectrum, and since the spectrum of this is going to be only imaginary, you'll get a stable network over here. Again, I didn't talk about how to discretize it, at least on the continuum, okay, and in the case that this is continuum. The other thing is, when we start looking at this, we start thinking, okay, I mean, what do we do in physics to get well-posed type problem? We basically have things that look like Hamiltonian networks. Can we generate something which looks like a Hamiltonian network over here? And the answer is yes. I mean, very straightforward. We add a dummy variable here, z, and then what we do is we just have this kind of system over here which looks like a Hamiltonian dynamics. It's not exactly Hamiltonian dynamics. Again, there is this nonlinearity over here that happens, but it has, let's call it Hamiltonian dynamics inspired, okay? And you can come up with integration techniques that will come up and do these kind of things. And of course, these two networks in particular are in principle not lossy. You don't have any diffusion on them. Lars will talk after me about the idea of adding diffusion, because diffusion may be very important for some problems, okay? Now, the good news for all these kind of things is that the people in that particular community invented a lot of known names to things that you already know already. So I'll try to go over things as I go along. If you want to be rich and famous, you can invent your own, whatever architecture there is. You'll have it under your own name, and you'll be rich and famous if it works for you. Okay, so that's something to remember. Okay, now we talked about continuous stability, but discrete stability is a little bit different. Now we discretize that thing. So for example, if I use these networks, which have completely imaginary spectrum, and I would use forward Euler, which is the standard discretization that exists, I'll be in trouble. Why? Because we teach this thing in the first course in numerical analysis. This circle should have been familiar to a lot of people when they teach this thing, and they say this is the region of stability for the forward Euler method. So forward Euler method, if you look, this is the imaginary axis, this is the real axis, is completely unstable. It's like unconditionally unstable for a problem that have only imaginary eigenvalues. So if I would use a typical standard, basically discretization, which is going to be a forward Euler on that particular network, I would obviously be unstable because I'm going to have imaginary eigenvalues. So in that case, I should not be using the usual forward Euler, and I can come up with different methods. So for example, we can come up with an Adam-Bashford 3 method, and we can actually come with a lot of them. So here is 1, 2, and 3. So stability of 1, stability of 2, stability of 3. This is the usual Euler thing. And now you're getting, other discretizations that are more stable on the imaginary axis, which is what you really want. So that implies that, for example, if you think about a usual neural network, which use only one step backward, here we actually introduced a neural network that uses 2 steps backward. It's a multi-step integration technique, and we are basically using this particular type of network. So here we came up with a new architecture for a neural network that is stable to start with, and again, it works not necessarily, it's not obvious, correct? I mean, you would not look at a neural network and say, oh, I should use basically a weights of 23 divided by 12, and then 16 divided by 12, and 5 divided. This is not something that you would come, obviously. You have to open Uri's book on ODEs, you look at your favorite method, and you come with this. And it doesn't have to be the only method, correct? I mean, that's the other thing. So for the Hamiltonian one, most of you have seen Varlet integration techniques, and you can come up with basically a half-step method that does exactly this. It's in principle supposed to be a symplectic integration, and basically it's supposed to work for you if h is small enough. So we have to pick h, remember, it has to be sufficiently small in this case. Okay. Now, again, I told you this field is completely open right now. The only people who are not using other methods besides the forward Euler method right now is there is one group besides us, and there are us. So there are 2 groups. So there's a lot of people here. You can use whatever you want, and as you know, there is a zoo of ODE solvers. So you can use Ranga-Kata methods, and not to talk about implicit methods, which are right now a big question if you can ever use them or what to do with them. And I encourage people to try to get into this and to do more than what we can achieve. Correct? So there is all these different ODE solver will lead to different network architectures, which are not obvious, correct, when you're doing these kind of things. And you can use your favorite ODE solver and think with your other things. So again, one of the things that are interesting in this particular field, or a little bit different, if you're working on Navier-Stokes equations and you work on a control problem with Navier-Stokes, you're stuck with Navier-Stokes. That's what you have, correct? Here, you don't like the network, change it. Okay? Nobody says you have to work with a particular physics. You can change that particular thing. You don't like, you want to add diffusion? Add diffusion. It's your thing. See if this is really changing the final results or not. So we can explain now a lot of things in these kind of terms, but the point is that you have a lot of freedom to choose things in a particularly correct way, and not to choose things and say, I'm just going to try randomly picking weights and numbers and see if it works or not. Okay? We come up with non-computational mechanism to change things. Okay. Quickly to talk about optimization, not going to say much, but people heard a lot about backpropagation. For those of you who have been working in numerical methods for ODE, it's just the adjoint, okay? But as I said here with Aldo, the hype, so people about backpropagation said, it's like the brain, just the adjoint, okay? There's nothing more. If you ever computed the adjoint, that's what it is. There's nothing more than that, okay? So if you know the adjoint, you know how to do this, and you can compute the gradients. You can do, if you know how to do the adjoint, you can compute steps like the inexact Gauss-Newton methods. You can do all these different things that you have known from other places. Okay. Now when you have interpretation like this, you can do a lot of other things. You can do multi-level optimization. So for example, you can refine your things in time gradually. You require smoothing K and B, so I'm not going to talk about it much, a little bit, but how you require smoothness of this in time. And you may want to use inequality constraints to bound K to satisfy stability. So there's a lot of things you want to do. So let me give you one example, which is a little bit more or less interesting. I don't know, but we'll see in a second. So I want to show you first thing. Okay. So this is applying. How do I stop this thing on time? Okay. Let me try to do this like this. No, doesn't want to do this. This is more difficult than I thought. Okay, so we have 5 colors in here, and it's a little bit hard to see, and there is a square here, and you'll see that there is purples. So again, X, Y color, but now I don't have only two classes, I have 5 classes, And this is really difficult in the sense that the whole thing is not convex. I mean, you have something that, you know, the purples are around something and then they're there. You have these I don't know, what color is this? Red would be here and here. So there's all these different things here that have this strange shape, and you want to classify them. And what we've done here, we just use the Microsoft ResNet. So this is Microsoft ResNet as it came out of the box. So you can take it from, a TensorFlow implementation exists on the web. You can just download it and try it. So that's what we did. We just tried on this particular one. And the interesting, and we drew a box here so you can see what happened to the dots as you do the classification. And you are basically see that the whole thing spreads and it widens. And let me stop before it ends. And now, in principle, if you actually pass lines like this and like this, you'll be able to pass 5 lines here, more or less, and to classify this thing pretty well. So the classification works, but you see what happened, and the reason we plot this box is because things spread outside of the box quite significantly. Some of the yellow points went to one side, some to the other side, so you can start thinking that generalization here may not work that well. And we can show that in some cases you get some very strange lines in this particular thing, so you get some very interesting things that come out of this. Now, when you apply slightly better or a different algorithm to this particular problem, so that's our implementation of the whole thing. I'll try to stop it on time. No, it's a bit difficult to stop it on time. And here it's almost done. Okay. So you can see that first things stay tight because, well, we use a symplectic integration technique here on an ODE that is basically, well, it's not exactly symplectic, but it's close. And what you see is that things are not really moving that far away, correct? That's what you're getting. So no instabilities. And of course, because of that, things are not spreading too much, and it's much easier to find these particular lines that are not really going to be spreading all over. That's really the gist of this particular method. Okay. And that's what it's really doing for you. I will close this now. Okay, so again, this is what happened. You see this, so these lines that you get from here, you see these purple lines is things that you get when you do unstable classification. So you trace back to the points and you see where is it, which area becomes where, and you see that if you do unstable classification, you would get some of these really strange purple lines appears in some places, which means that, again, I would deviate a little bit from this yellow point here, and I would go here, and I will suddenly classify it wrongly. So these are things that you see even in 2 dimensions. And again, when the space is dense, think about trying to sample points, sample spaces of 1,000,000 dimensions. I mean, how well can you sample them? So this becomes really a problem. Okay, and stable classification, you don't see all these things. I mean, you see that basically it's very straightforward. You don't really see any big problem. The only problem you may see is here, but this is outside, completely outside of our data region. So this is where things happen. Okay. So again, so this is just on the stability part. The mesh continuation is now you have a continuous structure, and one of the reasons we like continuous structure is not only you can explain them, you can actually take advantages computationally on these kind of things. And one of the things that you can do, for example, is very natural to what we do in every multi-level methods. We say, okay, rather than discretizing things with 1,000 layers, let's start by discretizing with 10 or 4 or something like this. And then you say, I solved the problem on 4, I'll do continuation, solve for 8. I'll finish for 8, I'll do continuation for 16, and so on. Maybe I want to stop at some point. I don't want to refine forever. And it will tell me more or less where I need to stop because I'm not improving, for example. So when we know these things, I mean, we've done this thing in optimal control, correct? I mean, these are not new ideas. It's just taking the ideas that we have from optimal control and doing it over here. So this is, again, mesh continuation in time. And just to show you one example that Lars actually will talk much more about, and this is really a PDE example because now we're talking convolution, but that's not my turn to do this. So we look at MNIST data. By the way, MNIST data is a really great place to start for anybody who wants to start because everything works on it, okay? So when you try, it's really encouraging. Like you get your algorithm and it works, and you're really happy that it gives you the right results. So that's really good. There is another data set which is called CFAR10 where nothing works on it. So, you know, this is always good to start with the one that you feel good about what you're doing. So this is the one that, you know, when I show you good results on it, don't get too impressed. Everybody can make it work, okay? So it's a toy example. It's images of 28 by 28 of digits. So they give you, I think, 40 or 50,000 of those. And what you want to do is you want to go ahead and to learn this thing from handwriting. And then when I show you a new image, you want to basically predict what it is. That's the basic idea. So these are just some samples of these handwriting pictures that people have, and I mean you can see the variability here. So for example, some of the difficulties will be usually you see the 7 and maybe 1s, so 1s and 7s sometimes will get confused a little bit. So you can see that it's not, I mean, it's not hard, but it's also not completely trivial to do this thing. And that's what you want to achieve here. So the results I'm going to show you are just looking at what happened when you do continuation versus what happened when you don't do continuation. So if you do continuation, let's look at so there are two things here. Let's look first at the objective function. Let's forget this thing quite completely, just look at the objective function. So what happens? You basically look at 2 layers, so only 2 layers, not much, and you see what happened to the objective function, you basically decrease. So we use this one, the difference between the red and the blue is that how you initialize your weights. If you initialize them in a random way, you can get different results. And you see that in this case, the realization of the blue was doing a little bit better than the red. Now what do? We take the solution and we do continuation. So we go to 4 layers and we do smooth interpolation because again we want smoothness in K, and we do a smooth interpolation from the 2 layer to the 4 layer, and we reinitialize our problem. So clearly, by the way, we converge faster, but we're not really trying here to actually talk about computational speed. But you see it goes a little bit up. For those of you who've done multi-level, you know there's interpolation error, basically the high frequency components. And then you're basically going down and basically getting to a result, which is, by the way, here a little bit better than what happened if you start from scratch. This is every time we start from scratch on 4 layers. Okay? Then we do, again, we go back again, we go to 8 layers. The bump is a little bit smaller, and we do this, and then we do 16, 32, 64. And you see, by the way, that probably from any point of practical assessment, you would probably want to stop here anyway because this minimum and this minimum are basically the same. So there is really no reason for you to continue. Maybe one before, I don't know. And here you just start from scratch every time and you get a slightly worse objective, which is again typical for those of us who've done multi-level optimization. When you look at the validation accuracy, which means how well does it work for a data set I did not use, well, you'll see that in the beginning this was a little bit better, then a little bit worse. Most of the time it's worse. Once you get lucky, so you could get lucky, because you start from scratch, who knows, you may get lucky. By the way, even though, as you can see here, the objective function is not doing as well, correct? So this is the training. Training here is doing worse, but the classification, or on the new data sets that you have not seen, you're doing slightly better. But again, these are very close, and but at the end of the day, again, the minimum is better, so we converge a little bit faster, and we get some better minimum usually. And you also know more or less where you want to stop. So again, this is a really nice advantage of this whole method. Okay, so I want to finish because otherwise I'll be above time. And I want to really think to finish the whole thing of trying to let you think that all this deep neural network, it's that everybody says is going to take everybody's job and all these other things. It's a simple dynamical system. The usual theory on this works. When I started working on this, I talked to a bunch of people and they told me, everything we have done in science, nothing really applies here. Nothing really works. And I claim the other way around. Everything we've done in science works. So we all know that when you work with unstable stuff, unexpected things happen. We work with stable stuff, expected things happen. So the usual theory actually does work, and we actually have some theory. We need to change for this the architecture. In some case, we can come up with better architecture for this. And again, we can actually maybe add better optimization algorithm. This is what we're working on these days, trying to team it with better optimization algorithms. And the extension of PDs, which is a much better talk, is going to be after my talk. Okay, I'm done.
Thanks a lot, Eldad. Questions? Yes.
Hi, nice talk. So do you think that this is sort of an explanation for how batch normalization works?
So batch normalization is a hack in some way. Batch normalization, what it does, it tells you basically you propagate too far, correct? So I say, don't propagate too far. I mean, go back. So what you're trying to do is you're trying to prevent, basically what you're doing, you don't have a network that by design is doing a good thing. So you're trying to do by brute force, you're trying to take the network in the optimization step, by the way. I mean, there's no, in the optimization step, what you're trying to do is you're trying to, in the optimization step, try to pull it back all the time. But even with batch normalization, you may not necessarily get something, it's stable for, of course, the data you're using.
Stable for that data.
Yeah, but it's not going to be necessarily stable for anything beyond that. That's the problem. Yes.
Hi, you mentioned that some deep networks use the same nonlinear function sigma at each layer, and others do not. My understanding is some use dramatically different ones. Like you might have a softmax kind of right in the middle of a bunch of others. Is there any way of interpreting that type of network in terms of ODEs?
Yes, I mean, this is actually not a problem in some way. I mean, you can think about, nobody says the function, let's go back to somewhere here. So I look at this function sigma, I mean, as long as I can make it piecewise constant from time t1 to t2, and then from t2 to change the function, correct? I mean, we have functions that are changing. There is no reason why we could not be doing this. It depends on what you want to do. I mean, again, don't forget where it's all coming from. There is a question, do you really need it, right? When you have no direction, when you're saying, I don't know what this thing is doing, so what do people do? There is actually a friend at UBC that in his PhD was running these things in batch, in parallel, overnight, on big computers, trying everything, right? So I don't know what this is doing. Why should we use sigma 1 to be something else, on sigma layer 2 will be something different, and we'll just batch it all overnight, we'll see what gives us the best result, we'll wake up in the morning and we'll say, these are the best parameters. People use Bayesian optimization, there's more sophisticated than this. So basically they're batching run things overnight. If we understand it in this form, do we really need to change the function? That's the question. So by the way, people who know me around here know that my mathematical abilities are very weak. So I have no understanding really of analyzing, nonlinear dynamics of. I mean, I did a course once of nonlinear dynamical systems, but understanding nonlinear dynamical systems very deeply is not my field. And I think that it's going to be a great impact for people that understand dynamical systems much deeper, and looking at this and understanding what do we actually need in order to make it work, and what kind of function, what kind of nonlinearity, does it change, does it not change, is it piecewise? I mean, all these are open questions. That's why I think it's such a fascinating field right now.
Yes. So to put in this context of a dynamical system, you normally think about fixed points. In other words, you now have your recursion relationship. And to what degree have you tried to identify fixed points and see how that's related to the final things they evolve to?
So first thing, for some networks, it's obvious that you can think about fixed points. In some others, it's not so clear. But again, I'm more thinking about from a control theory. So to me, it looks like a control theory where you actually have a dynamics when you go from one point to the final point. So you don't necessarily want a stationary point. You want to have a dynamics. It's like I'm planning a trajectory, correct? I'm trying to get from one point to the other under some constraint. And this is usually, for me, that's the interpretation. It's not a fixed point that I really care about, because the fixed point will say that I'm not moving anymore.
No, but the point is, you start somewhere else. If you have a stable attracting points and some initial condition that wherever you'll start will be attracted to eventually this fixed stable points. And so one way to find out about the fixed points is to precisely to do this forward evolution, but you will miss all the unstable fixed points.
Yes, again,
But anyway, so I just want
No,
to
so I've not analyzed.
Think about if you already have a way to analyze these set of fixed points, that might give you some insights about the number of a classification you can do. Possibly.
So, I mean, again, one of the things that I looked at the beginning was looking at fixed point, because that's the obvious. I mean, as I said, I took one course in dynamical system as a graduate student, so that's the obvious thing that you do this. But it's not clear to me that you want to get to a fixed point. That's not. I mean, it doesn't look to me that what happens here is that you get to a fixed point. Let's say you have 10 different fixed points, and 10 different fixed points will correspond to 10 different classifiers. That does not seem to be the issue here. That does not seem to be what you have. So it seems that if you continue evolving the dynamics, you will continue going. So I think it's a little bit different, but again, I may be mistaken. It's not.
We can chat later.
Well, you talked about diffusion, which means indication of a PDE. So where does this come into the...
Well, you have to listen to the next one.
Which is the other group you said?
Sorry?
Which was the other group that is looking...
So there is now a group in Princeton, so Wayne and E is looking at exactly this kind of dynamics and published one paper on this.
It's just a comment. So there's very recent work by a group from UCL, which studies generalization using like Lipschitz properties of the whole network.
Okay.
Very related.
Okay. Again, as I said, the field is moving so quickly that it's hard to follow on everything, but if you give me the reference, I'll be happy to look at it.
I mean, the architecture is based on taking many small steps. I mean, the typical computation person in your network will tell you, I don't care, I take 10 layers and I do them as I want. So how what can you say basically? I mean, how does stability? I mean, if you take a fixed number of layers, there's always stability somewhere. You can't do anything wrong. How would you translate your?
So first thing, I would claim that this is not true, and I would just show you this picture, correct? I did not invent this picture. It's not me. That's coming from other people. So I would claim you have problem of stability.
You have problems of stability, but the question is, do you explain them with the usual Eve theory, or is it?
So again, I mean, when you have 10 layers, it's something to the power of 10 that you have to really think about, right? So 10 layers maybe not sufficient to generate stability problems. If you look at people in like Microsoft right now came with 1,000 layers. You're starting to really look at these kind of things, and people talk about again, I wouldn't, if you have a 2-layer neural network, forget this. You don't need all these kind of issues. This mechanism is way too. I mean, who cares about the ODE when you have 2 steps, correct? I mean, you have to think about when you have like serious number of steps. I mean, 10 is close, but now people are using easily 100 is a very common network. So this is where you actually start thinking about bridging. Correct? I mean, again, we always talk about h going to 0, which means that number of steps goes to infinity. What is 0 and what is infinity? As numerical people, we know that this is a little bit different. Now, the other thing which is something I did not show. So all these h's really mean because we're using explicit methods. There would be a different thing if you use some kind of an implicit method, semi-implicit or something that we can actually take now very big steps, correct? There's not going to be a limitation. So we have work right now on a semi-implicit method for this, for a particular structure. Once again, not for every structure because it can be very complicated in some structures. And then you're not limited by the step size, as you just mentioned, which is a problem. I completely agree.
But I mean, the other question is also, what does the h mean somehow? This only means something if you constrain some of your K2 matrix.
Yes, so you have to, for example, constrain. So h times K2 lumps together, correct?
Yeah, right.
So what you really care about the stability is, of course, what is h times K2. So if you determine that h is, for example, 1, then you may want to take the K2 to be to a certain. You can add band constraints, correct? All the entries of K.
You will do that in the optimization.
Yes.
So if you don't mind, I can see that the discussion could go on for a long time. And I thank you very much for your